In this video, we're going to talk about properties of estimators and why we care about those properties. I should say that these are only some of the properties that an estimator might have. We're going to talk about unbiasedness, consistency, efficiency, and whether or not the estimator has a known distribution. So, as a refresher, a statistic is a function of our data. For example, if I use T, so this is T1, which is just some general statistic, and I can calculate the mean by adding up all of the data and dividing by the total number. So the statistic is this mean, and T, this is the letter I'm using for the statistic. Sometimes when you see this, people will write like this X with the little vector to denote like a bunch of data. So here's another statistic. If we take the minimum of all those X values, or we could take the first value and just use that as our statistic. And we should be careful to note that like X with like a little parentheses around it and a 1 means the minimum value. But without the little parentheses, it just means the first observation. Here I've done a more complicated sort of statistic. You guys should recognize this one. It's all just a function of the data again. And sometimes you could just have the statistic be all of the data itself. You don't even need to do anything to it. Oh, I wrote this last one because it's just fun to be weird and complicated. So when we're talking about estimators, we're talking about a statistic that we're using to estimate some population value or a true value. So examples of this would be the population mean, we would use the sample mean, or the population variance, we would use the sample variance. And when we're doing regression, we have our betas, and then we're going to have our estimators for them, which are, again, functions of data, all of these things. And then we have our error, our variance, and our estimator for that is the MSE. When I'm writing about estimators, I'll probably use this generic parameter as just like theta, and then the generic estimator of it is going to be theta hat. Estimators are also sometimes called sample statistics, right? So I should put that. Estimators have a distribution, right? If we take multiple samples of and we create multiple different statistics, right? For every time I take a sample, I'm probably going to get different values, which is going to give me a different value of my estimator. So we don't usually do that. We don't usually like draw multiple samples and then plot them and then get the distribution, but we can use things to imagine what it's going to look like because we can quantify how much variability there is. And then we can use those properties that we know about, the statistical properties, to draw our distribution for our estimator. So an example of this is one that you guys have done many times, I'm sure. So let X be the weight of a hippo, and we're going to say the hippo weights are distributed normally with some mean and some standard deviation. And we're going to take a sample of 10 hippos, and we find that the average hippo weight is 2,016 pounds. If I had taken a different sample of hippos from the whole hippo population, I probably would have gotten a different X bar. But we know a lot about the distribution of X bar, about the distribution of a sample mean, right? We know that if the population is distributed normally, this is also going to be, this sampling distribution, or the distribution of X bar, is also going to be distributed normally. Its mean is going to be exactly in the same place, right around mu, and its standard deviation is going to be the original standard deviation divided by the square root of n. Another thing about this is that when we choose an estimator, we want the error of the estimator, so this is the standard deviation of the estimator, we want that guy to be small because then there's a better chance of getting a sample or a statistic or an estimator close to mu, the thing that we actually want. Another good thing about this is that we know that this statistic here is going to be distributed t. So these are all things that are going to help us. So here are some properties we might want. One of them is unbiasedness. And if your estimator is unbiased, it means that if you have lots of values of the estimator, that on average, they would be centered around the truth. So you can see in the middle of my bullseye, I have a little theta. That's the true value of theta. And these estimators, if I took the average of all of them, I should get that if I did this sampling many, many times. So recall that if I sample from X bar, many, many samples of X bar, that on average is right in the middle is the truth, mu, the population mean. So that's an unbiased estimator. When we have an unbiased estimator and we take the average, the expectation, we should get the parameter. So this is the mathematical definition of unbiased. Another property we might be interested in is consistency. A consistent estimator is one where as your sample size gets large, the variability of your estimator around the truth shrinks to 0. So let's take a look at what that looks like. When we only have a few observations, so it's not that there's like 10 little theta hats, it's that each theta hat is made up of 10 observations. They have quite a wide variability. When we get more observations, when we get 50 observations, so each theta hat is made of 50 observations, then they're getting closer and closer to the truth. 100 observations, they're shrinking. 200, they're shrinking even more. And then finally, when we get to an infinite number, we should get that they're exactly the same. If we were writing this mathematically, this is how you would write it. Some of you may see this. Efficiency is another really nice property for our estimator to have. An estimator is efficient if it has the smallest mean squared error. So just to recall what mean squared error is, right? We find the error between the estimator and the truth. We square it, and then we take the average. It turns out that the MSE is the variance of the estimator plus the bias of the estimator squared. Here's some estimators for the average hippo weight. So that would be the mu. We're going to take a sample of 10 hippos, and then we're going to try to estimate mu. So one possible estimator would be the median. Another one would be the mean of the 10 observations. A third would be just looking at the 10th observation. And a fourth one would be the number 6. So let's look at the number 6. The number 6 has a very low variance, right? It's got a variance of 0. But it's probably really biased, right? It's very far from the true mu. The average, so the sample mean, this is unbiased, and it has a variance of sigma squared over n. We know that. We have our statistical properties. The 10th observation is also unbiased. It has a variance of sigma squared, so it has a higher variance than our mean. So we probably prefer the mean because we want smaller variance. And the last one we're going to look at is the median. So the median in this case is also an unbiased estimator because our distribution is symmetric. The mean and the median are the same. So the median can also actually be used here as an estimator of mu. It's unbiased, but its variance is not as small as the variance for the sample mean. A spin-off on this is asymptotic efficiency, which is to say that maybe our estimator at all sample sizes is not efficient, but as our n gets really big, then our estimator is efficient. The fourth property I wanted to talk about was that we know the distribution of our estimator. A fourth property that could be useful to us is if we know the distribution of our estimator. If we know the distribution of our estimator, that's going to help us to get those hypothesis test and confidence intervals.